Have you ever tried to fit as many shows as possible into a weekend and realized that no matter how much you shuffle the schedule, you always seem to be trading one thing for another? Add one more episode here and you lose something else there, and it feels like the schedule is pushing back against you. What you just experienced is what we call in the math world as a constrained optimization problem. You had something you wanted to maximize, which was your number of shows, but a rule that you couldn't break, which was the hours in a weekend. Lagrange multipliers are the mathematical tool that tells you exactly where the best answer lives, and more importantly, why it has to live there. Think of a function f of x and y as a landscape. Normally, you climb uphill to the highest point. Now let's add a constraint. You can only move along a curve g of x and y equals to 0. The global peak might be off limits. So what's the best point you can reach in this case? Well, let's look at the level curves of f. Higher curves mean better values. You want the highest one that still touches your constraint. At the optimum, that curve doesn't cross the constraint, it just touches it. They're tangent. Gradients are perpendicular to those curves. So if the curves are tangent, their gradients must point in the same direction. That gives us the condition del f is equal to lambda del g. Lambda is just a scaling vector. Let's make this concrete. We want to maximize f of x, y equals x squared plus y, subject to the constraint that x squared plus y squared equals 1, a unit circle. We need the gradient of f equal to lambda times the gradient of g. Computing the gradients, the gradient of f is the vector 2x, 1, and the gradient of g is 2x, 2y. Setting them equal component by component gives us two equations. 2x equals lambda times 2x, and 1 equals lambda times 2y, plus the constraint itself. From the first equation, either x equals 0 or lambda equals 1. Let's handle both. For our first case, x equals 0. Plugging into the constraint gives y equals plus or minus 1. So our first two candidates are 0, 1 and 0, and negative 1. Our second case, lambda equals 1. The second equation gives y equals 1 half. Plugging into the constraint, x squared equals 3 quarters. So x equals plus or minus root 3 over 2. We have two more candidates. Now we have four candidates total. Now we just have to evaluate f at each one. At 0, 1, f equals 1. At 0, negative 1, f equals negative 1. At plus or minus root 3 over 2, 1 half, f equals 3 quarters plus 1 half, which is 5 quarters. The maximum is 5 over 4, achieved at both points where x equals plus or minus root 3 over 2 and y equals 1 half. Notice we never needed lambda's actual value. Lagrange multipliers show up everywhere. In physics, they call it the principle of least action. In economics, we would call it the shadow price. In machine learning, the geometry of support vector machines is built entirely on this idea. Every time something is being optimized under a rule, either in nature, in markets, in algorithms, Lagrange multipliers are quietly at work, and you've just seen why. Thanks for staying until the end of the video. These are just some cool visuals I cooked up to show you guys more about Lagrange multipliers. As you can see, if the gradient of f partly points along your path, you can still move and improve because you're not at the maximum. You only stop when the push disappears because that's what happens when the gradient points fully perpendicular to your path. That's what we call the optimum. At this point, the gradient of f is just a scaled version of the gradient of g, and that's the Lagrange multiplier.